Test 1 2. Fine. So I'm screen recording this and also audio recording this on 2 different softwares while I'm presenting. And yeah. So some ground rules. If you have any questions, just put it in the chat. If I call out your name, you can ask the question, or you can just put the question in the chat itself. So we will start with, we have a few things that we are going to do today. One is I want to start with geometry. Then we'll proceed to light, and then Fermat's principle and differential equations. These were the these were not the 4 topics. There were some other topics. I added geometry right now because I thought that makes more sense. And what was the topic? Light, Fermat, optics. Yeah, light and optics go together. And while I'm doing this, I'm going to start with grade 7 and 8, and then proceed to grade 9 and 10, and then grade 11 and 12, and then probably goes to graduate level and then master level. I'm not going to tell you when the transition happens. You probably will figure it out whenever that is happening. And if you don't figure it out, then I'm doing a good job. So the first thing is I want to talk about geometry. And my first question would be, you have like 2 of these points. You have 2 points, and what's the fastest route between those 2 points? So hold on. Yeah, I'll be shifting a lot of tabs. You'll have to just understand where I am. Okay. So basically you have a parking lot, you standing over here, your car is over there, and you need to go from your point to the car in the fastest possible time. Probably the front brakes or the hand brakes just failed and it started moving. You need to get over there to open the car. Someone is stealing the car, something or the other. You need to reach there as fast as possible. Which is the fastest path from your point to the point at the car? What do you guys think? Anyone with the answer in the chat? A single straight line is the shortest point distance between 2 points. That's what Shruti is saying. How do you know that? How do you prove that? Okay, how do you go about proving that the shortest path between 2 points is the shortest path between 2 points is a straight line? How do you show that? Displacement is the shortest, but it is again a straight line. But how do you know that the straight line, trigonometry, Aryan, how would you go about doing it? What do you think? You can, but that's just a method that you could use. What would the steps be? I'm not asking you to give the entire proof, but how would you go about going? This is the first thing I would do. This is the second thing I would do. Third thing I would. Okay. Some of y'all in the chat is saying like by using graphs and by measuring distance. See, by measuring distance, you can actually verify if one path is shorter than the other, but you can't prove it. You'll have to do it for all possible paths. And for all possible paths, it would mean that you have to do infinite measurements. It originates from the origin. Not necessary, Aman. It could be anywhere on the graph point. So let's look at that first. Alright. So let's look at that. Where is the share this tab? Okay. So you have these 2 points. And everyone is saying it's the shortest path is this particular path, but you can have multiple number of paths which goes from point A to point B. Let's go with that. So this is point A over here, this is point B over here. You can go this way, you can go that way, you can even go this way. Alright. Assuming you travel at the same speed, obviously this path is going to take the least amount of time. So first I want to prove to you that the line is the shortest path. And for that, we are going to use 2 properties. One is that if you have a circle, and this is point A over here, and this is point B over here, then we know that the circumference, the arc which is at this line over here, is going to be longer compared to this line over here. So the chord is shorter than the arc of the circle. The next thing is if you have a triangle, you have A, B and C, 3 sides. We always know that any side is smaller than the sum of the other sides. This is a property of triangles. Okay, so knowing these two, assuming we have a path like this, what you can do is you can convert any path into small arcs. So we can convert this path from here to here as a path of a circle. And you might have multiple proofs to actually do that, to do this thing. I'm just trying to go with simplest geometry. So as you can see, this circle kind of fits properly over there. Now, if this path from A to this A dash, let's call this A dash over here. If this path is an arc, we know that I can go along the chord. And this will be shorter compared to traveling in an arc. You can do this for every section over here. Okay, each of this is basically a part of some circle, and you will get a polygon like this. So any arc which is there can be converted to a polygon first, and if you have a polygon, then you have these two sides. I can always connect this side and I can say like, okay, we have a triangle over here. Instead of traveling along two sides, A plus B, where A and B is over here, we can just go along C. Okay, we know that C is less than A plus B. Then once you have this, we can make another triangle. And then this line is shorter than the total distance over here. Then this line is shorter than the other lines, and so on and so forth. Basically, you can prove that among all the curved paths that you have, the straight line is the shortest path. Okay. Someone will have to actually keep a track of the chat because I am losing it. Anyway, so is this clear? Like how, we can also prove displacement as shortest through, because vectors will also work for curve. Curve is made of points. Yes, it can. I'm just trying to go for the simplest proof. I know what you're saying, but I'm just trying to go with the simplest proof without using vectors and all. Vectors is always avoided in physics. It's too difficult to work with it. Alright. Okay. Next question that after this, if you have any questions, just like put it in the chat and someone just let me know that it's happening over there. Alright. Where did we go? Yeah. Next question is a simple puzzle that we have. Okay. This over here is Bob. Bob has a empty bucket of water and his hut is on fire. There is this beach over here where he lives. There is sea underneath. He has to go from where he is, pick up a bucket of water and then put out the fire. Alright. Now, if you look at this, do I have another sheet which I have created over here? Yeah. Yeah. If you look at this point over here, the left dot, this is where Bob is. This is where his heart is. And he has to go from point A to point B and extinguish the fire, but he has to make a stop somewhere in between to pick up the water. Now the question is, which would be the best place to go? So for example, he has multiple paths over here. He can run straight down to the river and then he can go to put out the fire. Assume these are straight lines. I'm horrible at drawing straight lines. Or you can go over here and then go to put out the fire. Or you can travel over here and put out the fire. How do you decide which would be the fastest possible way to go from A to B? Obviously straight line is A to B, but he has to make that stop. So now which would be the fastest path? How would you go about solving this problem? You need to go from where you are. I'll just show you the puzzle again. Okay. Bob is over here. He's on the beach. He has to go and fill up water from the beach, from the sea, and then put out the fire that his house is on. And he has to do this as fast as possible. Anyone? Third would be the best. But how do you know that? There might be another path. If you go for the midpoint, okay, that's kind of Yes, Mitesh. What kind of construction? Tell me. Okay. Okay. All right. So we'll go with that. I think so. I know what. And yeah. Okay. Okay. Haha. Okay. So what Aryan is actually saying is that, let me get this over here. Yeah. That if you just travel along the y-axis downwards, you're not making any progress along the x-axis. Okay, so the amount of time you take to go from point A to, like, from the where he is to the C directly, in that time he's not moving towards the right. But if he's taking a diagonal point, if he's taking a diagonal point, then obviously he's going to like make progress along the y-axis and along the x-axis, both of them. Okay, the question now arises. The question now is that which point does he go to make sure that he reaches over here in time? Okay. Mm-hmm. Okay. All right. So that's the right answer basically. But then how do you show that it's the right answer? From reflection of light. Okay. So what Sashank is actually saying is that out of all of these, can I make a duplicate of this? I should be able to make a duplicate of this. Ah, oops. I deleted it. Okay. So what Sashank is saying is that if you have A and you have B, then any point which makes equal angles, okay, so if this is 30 and this is 30, then that would be the fastest path. If you take the midpoint, that will not happen, by the way, okay, because this and this are not in the same level. If you take the midpoint, one might make 45 degrees, other might make, I don't know, 30 degrees or something like that. But the question is, how do you go about proving this? How do you prove that like this has to be the fastest path? One way of doing it, and I don't have anything over here. Awesome. Okay. One way of doing it is that we put some numbers over here. Okay. Small h is how far Bob is. Capital H is how far the hut is. And D is the distance between the perpendicular distance between both those lines. Okay. Aryan was saying that you make a reflection in the sea. So you make kind of an image of this hut in the sea at exactly the same distance how far it is from the bank, like where the river and the sand meets. Now my question is, like, from the left red dot where Bob is to the new image point in the sea, what is the path that he should take to reach in the fastest possible time? Would it be a curve or would it be something else? We had seen this before in the first one, the first problem itself. I hope everyone can hear me because everyone is silent right now. Straight line, yes. So you do make a straight line that goes from where Bob is to the image in the sea, and that would be the fastest path. But now if you look at the reflection, it's basically the same distance that he's traveling, right? So if you just project this line back onto the surface again, by similarity of triangles, you can say that this line over here, from where the intersection at the river is, or the C is, and this line over here, they are the same length. Okay, since the shortest possible time from Bob to the image is a straight line, and since this distance from Bob to the C and back to the actual hut is having the same length, it has to be the shortest possible distance. And just by similarity of triangles, you can just show that the angle would be equal, angle of incidence and angle of reflection, so to say, would be equal in this case. So, okay. So if you do that, you make a normal over here. Wow. Okay, you make a normal over here. Then this angle, whatever it is, theta, and this angle, whatever it is, theta, would remain the same. Okay, that's a geometric proof just by using geometry. How do you do it using algebra? Because we are going to basically convert this into a calculus problem to go from here and solve, get Snell's law, derive Snell's law. You all know Snell's law is basically observation, right? Everyone knows sin I upon sin r is a constant. How do you derive that? And that's what I'm getting to actually with this. So one way of doing it is that let's set up some geometry over here. We will solve for infinite cases. And I need you all to actually just bear with me for a bit. I said this is small h. This over here is capital H. Okay. This entire distance from here to here is d. What I'm going to do is I'm going to select different points over here. Okay. So as a general point, let's take this point over here. This distance, I'm going to call this as x. X is going to be my variable. This distance from here to here would become x minus x, sorry, what am I saying? This will be d minus x, okay, this distance. Now the total distance Bob has to travel would be this line over here. We will call this d1. And then from this point to this point, we'll call it as d2. Alright. Now, this is a right angle triangle. This is a right angle triangle. So let's look at this triangle over here. We can say that d1 square is equal to h square plus x square. Alright, so I know that d1 is equal to square root of h square plus x square. Alright, same way if we look at this part, we can see that d2 is d minus x square plus h square. So d2 would be square root of d minus x square plus h square. So we know what value of d1 and d2 is. So total distance that you have to travel is d1 plus d2. That's done. But we don't want to know the total distance. We want to figure out what is the shortest possible time. So we have to calculate the amount of time he would take. Now let's say he's traveling at some speed v. This is the speed that he can run at. And it's very constant. So total time that he would take. So we know that speed is equal to distance upon time. So time would be distance upon speed. So t1, the time it takes, so time it takes to go from here to here, we'll call that as t1. Time it takes to go from here to here, we'll call that as t2. So t1 would be d1 upon s and t2 would be d2 upon s. Okay, we know what d1 is, we know what d2 is. So capital D, the total time would be equal to d1 upon s plus d2 upon s. Alright. Now to solve this, let's make an Excel sheet over here. This is your x, d1, sorry, this is your Excel sheet. This is x, this is d1, this is d minus x, this is d2, time 1, time 2, and this is a total time. I'll call this capital T. So we know that d1 is from Pythagoras theorem. Let's see in that. So d1 is square root of h square plus x square. So let's do that. If you look at the equations that I put, are these equations. Alright, and I have just taken small h as 30 meters, capital H as 50 meters, and the total distance between them as 250 meters. Speed is 5 meters per second. These are just random values. You can change this and the entire thing would actually change. So what we finally get is that if you run straight down, the time it would take is 56.99 seconds. And we can do this for a bunch of values, okay, at 10 meters each. So x is 0, 10, 20, 30, 40, which in our case over here would mean that this x would be 0, 10, 30, 40, like that, right up to 250, and then up. We can even go backwards and go to that point B, but that we know it's senseless. It doesn't make any sense. That's definitely going to take more time. Now what I'm going to plot is how much time it would take depending on where your x is. Where do you run straight down? Do you run 10 meters away from the point? And then check the time. And if you draw this graph, you draw the chart. Let's see, can I fix this? Yep, I can. Okay, you will notice over here on the x-axis I'm talking about the distance from this point over here. Wait a minute. Yeah, so x is the distance from this point. As I'm increasing the distance, so if x is 10 meters, it might be over here, x is 20 meters, might be over here. So how much time does it take if x is 10 meters, and how much time does it take if x is 20 meters? So x I'm plotting on the x-axis, time I'm plotting on the y-axis. And you will notice that the time it takes reduces up to a certain point and then starts increasing up again. Now this is not a symmetric case because h, small h and capital H are different. But if you actually make this a symmetric case, then this also becomes symmetric and you get the midpoint. You only get the midpoint as the answer if both Bob and the hut are both equally distant away from the sea. If they are not equally distant away, then we would get unequal answers. Okay, this graph is going to keep on shifting. There you go. Okay. All right. Now, I think so. Who was it? Sashank or Aryan? One of you all said like you use reflection of light, right? Okay. All right. So Mitesh is asking, why don't we just find the shortest distance by calculating its minima? But over here, that's what we are exactly doing. By drawing the graph, we are looking at the minima. Minima point is where the slope of the graph becomes 0, right? So yeah, so if you differentiate this particular equation over here, wait. Yeah, if you differentiate this particular equation with time, so if you say dt upon dx and you set this to 0, okay, which means the slope of this graph is 0, then the answer that you get is sine I is equal to sine r, or I equal to r in that case. Alright, you can try this by yourself. I can send you all the proof later. It doesn't really matter right now. I don't want to put too much math. I think so it's already there. Alright, and you can do that with refraction also. I think I'll just put this much today because I feel like I will overshoot the entire quota of how much math you guys can handle. In fact, it's overshooting the entire quota of how much math I can handle, so I'm not doing it. And we'll open this up for questions and we can take up any kind of questions from here. Alright. The idea basically being, I just want to get to the final idea, is that if you have point A and you have point B, alright, and Fermat's principle, I'll just jump to the conclusion, just says that out of all the possible paths that light can take to go from A to B, any path that light can take, light will take the path which will minimize time. Actually extremizes time, but most cases minimize time. That's the point that we are going at. So Fermat showed that you only have one law to explain reflection, refraction, and rectilinear propagation. So I think so in grade 7 or 8 we have seen three properties of light. First property is light travels in a straight line, rectilinear propagation. Okay. Second one is the laws of reflection, where I is equal to R, then all three are in the same plane. And what else did we have? We had one more thing, sin I. So the angle of incidence and angle of reflection are both on the opposite sides of the normal. So these two are equal. And with refraction, we had sin I upon sin R is equal to constant, which is also equal to the velocity of light in air upon velocity of light in water or medium. And then we had normal, this thing, this is your I, this is your R, and all these three lie on the same plane, and angle of incidence and angle of refraction on opposite side of the normal. So basically you had to talk about 7 different sentences to explain how light actually behaves. But Fermat just put all of these 3 things in one sentence. Fermat just said light will go from point A to B, which takes the least time. Minimum time. Okay, with this one statement, Fermat said that you can explain this, this, and this all together, all using math. Now I haven't entered calculus while doing this, but you can use calculus and minimize, like someone actually pointed that out in the chat. And yeah, I'm just looking at the chat question over here. Fermat's principle basically talks about properties of light. However, like geometric properties of light, not diffraction and all this stuff, but reflection, refraction. The speed changes, yes. So if you just want to have a look at the problem, I mean, you can, so this is Bob over here. Okay, this is the C. And over here, this is girlfriend drowning in the water. Bob needs to reach the girlfriend to save her life, otherwise she's dead. Now there are multiple paths which Bob can take. He can go straight to the water and then start swimming towards the girlfriend, or he can run fast on the land and then start swimming down. But there is one point somewhere over here which will minimize the time for Bob, where he can compensate. So he can run on the land and then start swimming towards her. Okay, and if you actually do the math, it turns out that the fastest path that Bob can take will satisfy sin I upon sin R. If you draw the normal, this is I and this is R. Okay, it will satisfy that, where his velocity on sand upon velocity of water. So this, wherever, any point where this condition is satisfied, he will reach in the fastest possible time to save her. Alright, now how do you prove that? The same way that we actually did over here. So you actually calculate distance 1, distance 2. So this is your d1, this is your d2. Find out time 1, find out time 2. And the total time which is there is t1 plus t2. And then you find dt upon dx, set it to 0. This is your calculus part. Those who have not done calculus will not know it. But yeah, setting this equation to 0, like dt upon dt, minimizing, where does the rate of change of time become 0, will give you this particular solution over here. Alright,